So we're going to be taking a look at the classwork exercises for 2.3, 2.4, 2.5, one per team. You're going to be tackling those. I'm going to give you about 20 minutes in groups, and then we're going to come back together and you'll present your solutions. We'll talk through them and see if there's any questions about those sections in particular. Sound good? Okay. In the meantime, now I got to get the breakout rooms up and running here. It won't take me too long. Let's see, breakout room 1. You guys are team May. I don't know if you noticed, but in JetNet, I created an assignment for each of the next 2 problem sets, along with the investigation that's due on Wednesday. So you can see those there. So we have Anthony. Anthony's not here. John, Quentin, and Austin. Anthony's here. Yeah, Anthony's here. He was here. Right People here. Keep like dropping in and dropping out. I don't know who keeps dropping in and dropping out. You're giving me a headache here. Okay, so that's that group. Who's in this group? Stephen, Price, and Wyatt. Stephen and Wyatt. The Dream Team. Team Poll. Yes, the Dream Team. And then breakout room 3 is going to be Team Doc. And you guys are 2. So there's 2 groups that only have 2 people, but that's not the end of the world. I'm going to open up these rooms. You guys get in there, get working, and in about 20 minutes, we'll be back together. If you need anything, just raise your hand. Okay, so you've had some time to work on a problem in each of your groups, one from 2.3, one from 2.4, and one from 2.5. And so what we're going to do is each one of those groups is going to give a quick presentation on that problem. If you didn't get to every single part, some of them I know had a lot of parts. If you didn't get to every part, that's okay. It's not the end of the world. But at the very least, it gets us thinking and talking about these concepts. Now, I don't know if you've figured it out, but Chapter 2 requires being really fluent with Maple, right? And knowing how to do things in Maple. And so when I ask for a vector field, you need to know that that's really asking for a field plot. When I say a phase plane or a phase portrait, you need to know that that means a DE plot. And you need to know the code to be able to kind of pull that up. And again, I used to, when I taught this, I used to be like, have a quiz on how to do this stuff. But you've quickly discovered that the people who do it and do it repeatedly, you just learn the code because you do it time after time, right? And you just get better at it. Now, I'm not asking you have this stuff memorized, but if you have a really good organizational system for your notes and for like Maple files, I think it's a really good idea to have kind of a glossary Maple file where you could say all the things from Chapter 2, all the commands from Chapter 2. Here's an example of each one of those. That's a really smart thing to have handy because you know there's an exam coming up and you know I'm going to ask you to make some of these things and you know you're going to have to know the code for them. So make sure you've got access to that stuff, right? So let's start in section 2.3. And 2.3 introduced the idea of the second order differential equation that gets turned into a system of first order differential equations. And so 2.3 number 1, I gave you a second order differential equation and then a laundry list of tasks. So take it away, Team May.
Okay. All right. So for A, just used a guess of e to the st because that's really all that could fit here. And then we took, you know, y prime, and it's just s times e to the st, y double prime is s squared.
Cest.
Yeah, oh, yeah.
Anyways.
But then we subbed that back into the equation and took out the, kind of skipped the step here, but factored out the e to the st because that can never be 0, and just looked at the polynomial here and then solved it for s, and that's how we got our 2 solution.
Nice, nice. Now notice, I actually see that he used Maple to figure out what the solutions are. And by the way, there's 2 solutions for that, not just 1. But you have the solutions for that obviously generated through Maple. What I don't want to see is, here's the polynomial, right underneath it, here are the solutions. It's like, where did those come from? Did you just pull them out your butt? I hope not. I want to be able to see the work. And so showing me that you did this in Maple, that's perfectly acceptable for work, right? If by this point you don't know how to solve a quadratic equation, you got bigger problems than me getting angry at you. So proceed.
Yeah, I don't know why Maple doesn't show both the solutions. Whenever you do the isolate, it just does the one.
I have no idea why either. I would think that if you did solve that equation for S, that it would give you both.
Yeah, that's what my group mates were saying.
Yeah.
Said it does.
But I mean, you knew it was going to be the plus or minus, so you knew
Yeah.
it was two of them. So,
Yeah.
so you have two particular solutions that are guaranteed to be particular solutions for the system.
Yeah.
Cool.
And then just moved on to plotting them, and it said just sketch a graph. So I just did a simple plot and did the negative first and then the positive. And then it wanted to plot the velocity functions. So just took the derivative of first the negative one and then plotted that. And then took the derivative of the positive one and plotted that. And that's about all that stuff.
Cool.
Then breaking it into a system of equations, dy dt equals v was our first one, obviously.
That's a gimme.
Yeah, and then changed the second derivative to dv dt and moved everything over to the other side. And so it was a minus y minus 4 dy dt. And since we already had dy dt is equal to v, we just put v then.
Nice. And of course, if you were going to enter those for Maple to do anything with, you'd want it to be dy of t dt and v of t, right? You have to call them as functions, but what you've got there is perfectly fine for me to read and for us to read.
Yeah. And sketching the vector field, just doing a field plot. And that's kind of what it gave us, a really weird looking thing.
Well, you can tell just by looking at it where the solution curves are going to be moving really fast. Not near the origin and not along that kind of diagonal, but anywhere, out in quadrant 1 or far out in quadrant 3, those are really going to be fast moving solution curves. The one thing that I will draw your attention to, actually, Chris, before you go too far, go back to your vector field. Take a look at your axes that are labeled.
So y and v.
So the problem that you're running into is the first equation in your field plot is the dy dt.
Mm-hmm.
But yet the first variable that you give it a range for is v.
Oh, okay.
So those need to get swapped. So if you change that one to a y and the other one to a v, now take a look. It's a little different. It really is a fundamentally different vector field because Maple doesn't know. It just says, oh, okay, so that first equation must be your derivative of y, and the second equation must be the derivative of v. And the way you had it before, it just interpreted them backwards.
Oh, okay. I didn't know that's how it did it.
Yep, that matters a great deal. So whatever order you put your equations inside the brackets, or the right-hand side of the equations inside the brackets, that order needs to be the order that you name your dependent variables. So cool. Yay, we learned something valuable. Those are always the best mistakes to make.
Does it do the same thing here? So like, should I say y is equal to that and then v is equal to that first?
Let's find out.
Probably. Oh, looks the same.
It's interesting. It doesn't matter. For this one, it doesn't matter. The vector field, it does matter. The other one, it doesn't. Yeah, it's crazy.
So
and
yeah,
we can rotate that and spin it around. Ooh, look at you. You've given it an initial condition.
Yeah, I wanted to give it like one initial condition in quadrant 3, and then one in quadrant 1, and then one right at the where I thought was the equilibrium point. And
yeah.
So it kind of gave a nice phase portrait.
Yeah. So to be clear, this is not what I would call a phase portrait. A phase portrait is a DE plot, not DE plot 3D, but just a DE plot with multiple initial conditions. So you can see, kind of get a really good picture of what's going on everywhere. But yeah, this is a great DE plot 3D.
Cool. And we just said that the solution at 0, 0 is just going to stay there, and every other solution curve is going to get closer and closer to 0, 0.
And you can tell that because if you rotate it so you see the time dimension, you can tell everything's headed towards that red line over time. And no matter how you rotate it, everything's kind of headed in towards the red line. So cool, nice work.
And this one was doing just a scene of single initial condition, and so it's pretty much just a DE plot.
Yep. So that should look familiar compared to some of your further back up graphs. So when you graphed, if you scroll even further up, your yeah, there you go, a little bit further. There you go. So that solution right there, the e to the -2 plus √3 times t, that same solution you can get by doing a DE plot with a scene, because that's the only the y of t part of the equation, or y of t part of the solution.
Yeah, and we didn't do the last part because we got called back right before it.
That's okay. Nice work. So the last part is just to create a DE plot for the solution, and then comparing back to previous graphs. And so that's what we were just getting at, this idea that you can create a graph of a solution curve using DE plot with a scene, or you can solve the solution and then plot the solution parametrically. So just plot the y of t, just plot the x of t, and take a look at it that way. Either way. So nice work. Good job. So that was 2.3. And we also had group poll was doing 2.4. And I think you guys had 2 of them, but they were connected to each other, right? So it was number 2. And then number 4 says create a phase portrait for that same problem. So how did it go? You did the by hand method for solving it. Oh, yeah. Go ahead. Sorry.
I have a question.
Sure.
So for that phase portrait, you said you wanted more initial conditions. So how many would you like in like a question like that then?
Yeah, so with a phase portrait, the rule of thumb is you want to have at least one initial condition kind of in each quadrant, if that makes sense for the particular problem. Bare minimum, to just give you a sense of if you were over here, or over here, over here, over here, what would the solution be doing? And the more complicated the system is, and you only know this by taking a look at the DE plot, the more complicated the phase plane is, the more initial conditions you should include. So if you see some like really weird swirly things over here, and then there's like a V-shaped thing over there, then you probably want to plop in an initial condition around there so you can get a sense of what's going on.
Okay, I just wanted to know that was.
Hello, hello. My doggy came to see me. Okay, so take it away, team pull, and we're taking a look at the by hand technique for solving a system.
All right. So what you're looking at here is the by hand technique of solving a system. And I really think Bryce was very eager to share his thoughts on this one.
Yay!
Well, actually, sorry, Wyatt was very eager to share his thoughts on this one specifically.
Fair enough.
Sorry.
All right, so we started off by noticing that it was a partially decoupled system, meaning that there's 2 components to it, and in order for it to be actually like a fully decoupled system, each for example, the first part is a part of decoupled because it's dx dt equals 4x, and since the dependent variable is the only thing that's on the right side, then that's how it constitutes. But it becomes a partially decoupled system because this one right here, 3x plus 2y, has 2 dependent variables, so it's partially decoupled. So to do this, we do for the single variable, you do a separation of variables, and that ended up giving us 3c constant e to the 4t, and then you that ended up giving us x of t equals constant e to the 4t. You then in turn take that x of t, plug it back in for x in the bottom part of the system, And then to do this, we take the mu of it, and I can't remember what the method is for that, but basically we get the final equation. So our two equations we get, the one is from the original x of t that we got, and then the other one is from the one that we solved using the mu method.
Cool. So this is only possible if the system is partially decoupled, right?
Right.
If thing is not decoupled at all, if it's coupled completely, like you have two terms, x and a y term in both equations, this method does not work.
And if it's completely decoupled or just a decoupled system, we can use separation of variables to solve.
Yep. Yep. Super easy to solve those. Yep. So cool. So we wound up with our x of t has one term in it, and our y of t has two terms. And you'll notice constant 1 from x of t appears in both equations because we had to substitute it back into the dy dt in order to solve for the y. So nice work. So by the way, did you check it with Maple just to make sure? Oh.
Steve?
Oh, wow.
What's that?
Yeah.
Did we
What's
check it with Maple? We did not. We got a warning, so we decided to just take a risk. And since, I mean, we're clearly right, like, there's not even questioning our intelligence. So we just jumped in and plotted it instead.
Fair enough.
Yeah. So this is our plot.
Oh, so this is number 4, right? This is
Number 4, yeah, sorry.
the DE plot. Okay.
So yeah, that's what we did. We spent our last 5 minutes declaring equation and plotting it. It looks all pretty and stuff, and so we threw some lines on it, and they're pretty straight lines, which was kind of surprising. There's supposed to be
So
one.
what do you make of that?
The straight lines?
Yeah, because some of them look like they're following the red phase plane kind of slope field-ish lines, the vector field lines, but they're some of them look like they're kind of cutting through. Like the one in quadrant 2 looks like it's going straight when it should be kind of curving downward. So what do you make of that?
Well, we just figured that if we were to like do a field plot, we'd find that these would be very large arrows.
Okay.
So my personal inclination was to say that these are just very long arrows, I guess, in the field plot are very powerful. Like it's just moving really fast here.
Okay.
We didn't test that by like changing the amount of time or anything.
So what could you do in the DE plot right here to show these curves, not just from their initial conditions, which by the way, you have like an initial condition of 0, 5. Oh, sorry, 5, 5, right? So 5, 5. What could you do to show where that curve comes from? Not just where it's going forward in time, but how could you see, kind of looking backwards, where does it come from?
Could do like a -10.
Hey. Oh, yeah, you knew I was going with this. Nemoints.
It's 7 o'clock.
It is 7 o'clock.
It is correct, yeah.
Hey, look at that.
How pretty.
So he went about it. Notice there's 2 ways that you could smooth out the curves. One way is using the method that you just saw him use, which is the num points, which is, what would you guess that's telling Maple to do?
Can I guess?
Yeah, feel free.
Adding more points.
Adding more points to what? Points. I mean, there's a fixed number of points on this plane, right? Well, there's an infinite number of points on the plane, but what do you mean? Adding more points to what?
They're calculating more points within the frame. Yeah.
So its solution curve is based on more points, right? So more points means less herky-jerky in between. The other way you could do it would be to use what option in your DE plot? Does anybody remember?
Step size?
Yeah, step size. You could force Maple to use a smaller step size. So if you, zap that num points, erase that, and replace it with step size equals, and then we'll just start with like 0.1. Right, you do 2 if you want, and then step size equals 0.2, and then see what we get for that. Should be like 1/10 of the step size. And that's 100th of the step size. And by that point, you're like, well, that's a pretty smooth curve. So I definitely, when I say I want you to make a phase portrait, I want you to be able to show not just where the solution curves begin at an initial condition, but where they go and where they come from. And so if that means you have to kind of back time up and make time negative to be able to see them headed towards the origin in negative time, that's cool. This is a lovely example of a phase portrait because we get a sense of where all the solution curves are, right? And if I were to plop down my cursor at any other point on the plane, I'd be able to tell roughly where that solution curve came from and where it's going if you look backwards in time or forwards in time. Does that make sense? How's everybody feeling about creating phase planes for systems? Feeling okay? Again, I think it's a really good idea to have a sort of a glossary document of or an appendix document of all the different types of code that we use that we've come across and examples of different options. So for example, having that num steps in there, that's important. You don't want to be on the exam and be like, shit, I know what I want to do, but I can't remember how to do it. What do I have to do to the code to make it work? You don't want that. So definitely, it's a good thing to have examples of that so you can refer back to it. And it's, I'll try to include stuff in the notes that I post, but you don't want to have to go sifting through all of my notes and go, where did he do that one example? It's much easier if you have your own that you make, and making it makes you better at doing the skill too, because it's good practice. So, as I like to tell my students, especially this is true for like the lower level math classes, you tell them you can make the most detailed note sheet you want. And the students are like, okay, I'll make a super detailed note sheet. And by the time they're done with this like 4-page note sheet, they show up on the exam. And how many times do they use their note sheet on the exam? Yeah, like 0, maybe once. Mostly because, holy crap, there's so much information on this thing. But more importantly, by actually writing this stuff down and by encoding it, by inscribing it, you are learning it, right? And whether you're typing it in or handwriting it or talking it in, if you want to use voice to text, however you do it, by the inscription process is the way in which we learn, or one of the ways in which we learn, right? It's why it's way easier to learn a skill by practicing it a couple of times than it is by watching somebody do it. That's just the nature of the beast. Okay, so cool. So we got a chance to see a partially decoupled system that got solved using that kind of trick technique. And hopefully you saw in the notes the example of the fully decoupled system. That's pretty easy. It's pretty straightforward, the fully decoupled system. But if it's not fully decoupled or partially decoupled, we're dead. We have no method for being able to solve this. And I don't know if you've caught on, but even when we have our second order differential equation that we turn into a system of 2 first order, it's not decoupled because that first equation is always dy dt equals v. And so that's not a decoupled situation. So even when it seems like you'd have a decoupled situation, it's not. Okay, so that's the 2.4. Now let's take a look at Team Doc for 2.5, and number 2 at 2.5.
That would be my share screen here. Okay, so we started out with, well, we didn't type it in at all, but we figured out that the 2 equations were dy dt equals v and dv dt equals minus v minus 4y over 2. And so those are the equations that we typed in.
And so notice that divided by 2 has to be there because it's 2 times the second derivative of y. So we had to divide that out in order to make that work.
So then we kind of plotted it to see what it looked like. This is what we kind of came up with.
So the only thing that I will note on this diagram, take a look at the axes, the way they're labeled.
Y, oh, should it be the other way around?
Now, keep in mind, the phase plane, it doesn't matter whether it's Y this way or V or Y this way, as long as they're different, right? This is Y and this is V, or this is Y and this is V, or this is Y and this is V. It doesn't matter how they're aligned. The idea that a plane can be described by two orthogonal directions doesn't matter what you call those directions, but every interpretation that you do makes a big difference, right? So notice the initial condition for that. Oh, okay, so the initial condition for that curve is 0, 2, 0. And on that plane, the one that you have right there, that means it's 2 in the Y direction and 0 in the V direction. The way you had it before, Maple interpreted that as 2 in the V direction and 0 in the Y direction. A very different situation. Based on the example that you were given, this way is correct.
Okay. Yeah.
Yep. So cool, you got it.
Okay. So then we desolved it, which I'm not sure we had to do. Then we put in EQ1, EQ2, all the Euler's method things here, and we tried it two different ways with like steps from like 0, 1, 2. Trying to figure out where I want to get here. We were trying to answer that last question of how is the choice of the delta t affect. Kind of came up to be the same thing, so we're not too sure about that. This is what we got anyway.
So what you're doing in the code there with the array is not determining the step size. You're just saying, hey, Maple, I want an approximated value at these particular t values.
Oh, that's
so,
true.
So what you have is essentially the same predictions for 0, 2, 4, and 6. And you'll notice they are exactly the same numbers. And that's because those two are using the exact same step size that you didn't tell Maple what to use, so it used its own choice, right? So if you want to use a specific step size, you have to tell Maple what step size to use. So part of the code for this is telling it what step size to use. And so if you do different step size for this one, so 0.5 for that one, sure. Different numbers, very different numbers, mind you. And then if you do a different step size for the one down there, so you'll notice wildly different results.
Yeah.
And based on the graph of that same initial condition, which one of these is more accurate?
Let's see here.
So your initial condition at 0, 2, 0.
I would say the one with the smaller step size.
Okay. So the only thing that I would warn you against is, remember, those two, the tables that you have there are giving you specific X and Y, or in this case, I think you have them listed as V and T. Yeah, the orders are flipped around, but either way, V and Y coordinates. Those two tables are giving you V and Y coordinates that you should be able to, if you wanted to, plot on a VY plane, and you'd be able to see where it's predicting the solution curve is headed. If you go up to your phase plane with a particular solution, notice your time is going from 0 to 10. If you back that off to 0 to 6, that right there is the best estimate that Maple can do with a very reasonable step size. You can tell it's a little bit kind of line segmenty at the beginning, but by and large, it's following the vector field pretty well. And so you can kind of get a sense of where that end result is. After 6, call it seconds, you can tell where the curve is on the phase plane. I would say it's like at negative 0.1 or something like that in the horizontal direction, and it's like at negative 0.2 7, something like that, in the vertical direction. That'd be my guess, right? And that means a y coordinate of -0.1 and a v coordinate of -0.7. That would be what I'd guess from the graph, from the DE plot. And now if we scroll down and take a look at those two tables, you can say at 6 seconds, the second one is pretty on. It's pretty good. But the first one, look at how far off that first one is.
Yeah, way off.
You're way, way off. And that's because you're taking big, herky-jerky steps. And so it's kind of all over the place. By the way, if you go up to your phase plane and force Maple to use a step size of 0.5, you could ideally see the prediction that that table comes up with. Does that make sense?
Yeah.
So you can force it to make a bad prediction if you want by using a big step size, or you can kind of visualize better and better predictions with more reasonable and smaller step sizes. Remember, Maple's doing all the calculation in the background. So there's so many calculations you and I we'd give up. There's no way we'd do all these calculations ourselves. So you could play around with another step size and say, well, what about like 0.0002 for a step size? And what you might find is it's not worth it, because the difference between where it was and where it is now is so small. For your purposes, it's good enough. Or maybe you want it to be even better, so you use it even smaller. And as you go, eventually you're going to reach the point where Maple goes, hey man, I can't store all of these decimal places. And then you run into the max fun limit. Yeah. The following errors occurred. If you scroll down, you see where it says max fun? Yeah. In other words, it can't keep all of those function values out to enough decimal places to make the calculations meaningful.
Yeah.
So there is an upper limit to how accurate our estimates can be. There really is. For the purposes of making a graph, no big deal. We run into that limit and nobody bats an eye. But for the purposes of making a super accurate prediction, I need to know the speed of this. I need to know the speed of this satellite as it's approaching orbit out to 5 decimal places, or else the thing blows up. Okay, well then it's time to hook it up to a computer that can handle that. So, how are we feeling about Euler's method for systems? Once you got the code, and you know kind of the bits and pieces of the code, interpreting it is the hard part, right? The code shouldn't be the hard part for you, because it's the same thing. It's just how you interpret the results that matters. Everybody looks like they're about ready to fall asleep, or they're looking at some other screen on their computer. They're like, sure, Steve, whatever. Right now I'm reading an article from, The Guardian or something. I don't know what you're reading. Anyways, any questions on 2.3, 2.4, or 2.5 conceptually? Big ideas or particular skills that you want to verify or that you want to touch base on in terms of the videos? So I'm looking at the YouTube page, my YouTube channel uploader page, and I'm looking and it says number of views for these videos. So section 2.5 part 1 has 5 views. So let me see, that's 1, 2, 3, 4, 5. Bullshit, 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 bullshit. Hey, okay, so that means 4 people at least are full of beans. Either that or you were all sitting in the same room like a watch party and you had the popcorn and you're watching the video together.
I kind of looked into that and stuff because I thought I was really too, and I tested something. It only counts it as a view if you stick to like the last second of the video. So what a lot of people probably are doing is you get to that last 2 seconds in the video and then they hit the next one, and that's why it's not counting that.
Yeah, I know. I'm just giving you a hard time. I really enjoyed that. I like watching this. It took me a while to figure it out. The my wife does a lot of videos because she teaches a lot of online classes, a lot of stats online classes. And so when she first puts the videos up, she noticed some, weird behavior. One of the weird behavior is it'll like stick at certain numbers of views. And there's actually a really interesting reason behind that, but there's certain numbers that the view count will stick at because the algorithm that they use to determine legit views from like bot views, once it gets to a certain point, it's like, hold on, we got to check these, and it goes through and it checks the views, and so it doesn't increase the view count until it's gone through and checked those. So there's all kinds of interesting stuff in the background. But suffice it to say, when I look at the videos, I want to make sure that people are finding them useful, but I also go and check for comments in case somebody's commented. And apparently one of my former students just decided to wander into one of the videos. Did anybody see that? Did you guys see that? It was really weird.
Yeah.
It was way back in, I don't know, I might have deleted it. I can't remember if I deleted it or not. It's like
I think I liked
1.9.
it.
What's that? You liked
I
the
think I
comment?
like the comment or something like that.
You deleted your previous student's comment.
No, I didn't delete it. I just kind of like hide it because he was like asking me this really in-depth question about his business. And I'm like, really? So I sent him a message and I'm like, just send me an email. You don't want to, really? On a video, an instructional video? But I might have left it there because I think he gave me a compliment, and hey, a compliment's a compliment. So you got to hold on to that. But that was a little bizarre. But if you run into anything on the videos that either doesn't make sense or you're like, wait a minute, something funky is going on, you can send me an email or you can put a comment on there, and I'll try to address it. And usually what I'll do is I'll reply to the comment so everybody can see it. I'll be like, oh, yep, I fixed that. Or that's a good point. What I meant was this. So that's kind of nice for posterity purposes as well. So,
I
okay.
have a question, actually.
Yeah, sure.
I just remembered that I had this question, and now I can't remember because I keep forgetting I have questions about notes. One of the examples, you said that e to the st or something cannot equal 0.
Correct.
And why was that?
So an exponential base e, if you think about what the graph looks like for that, right? It's an exponential growth or it's an exponential decay. But if you back that up, the curve, you'd have to basically let the input variable equal negative infinity for it to be equal to 0. But negative
Okay,
infinity
y
isn't
equals
really
0.
a value. Yeah, exactly.
I was thinking x equals 0, and I was like, it's right there. It's on the graph. That makes sense.
Yeah, it's the output value for e to the st. It's impossible for it to equal 0. And it turns out it's not just impossible as long as s and t are real numbers. It's impossible for it to equal 0 even with complex numbers. So it's kind of interesting.
Fun.
Which, by the way, we're going to get into in the next chapter. We're going to dive into complex numbers a little bit. So if you thought, hey, how come we learn this stuff in pre-calc and then it never pops up later on? Well, my friends, it's coming back. In many ways, it's never left. It's always been there, offering good food at reasonable prices. Quick, what movie? Oh,
Wait, say it again?
he's
Overstock.
back. Well, in many ways, sir, he never left. He's still offering reasonable food, good food at reasonable prices. Nothing? No? Well, if you hang on to the end, I'll find a clip and I'll show it to you. But anyways, so what I thought we could do right now is take a look at problem set number 7, which is all about section 2.4 and 2.5. And you'll notice there are a couple of questions that are multi-part, but the first question is all about proving whether something is a solution. The second one is using an analytic technique. And so what I want to do is give you guys about 15 minutes, no more, in your teams to take a look at those, take a look at that problem set. If you haven't started it, this is a good chance to kind of draft a sort of this is my plan for solving this. If you've already started them, then good, then you have a head start on this. But take a look at those. There are 1, 2, 3, how many questions are there on that one? Good God. 1, 2, 3, 4, 5 questions. And some of them have to do with Euler's method, and some of them have to do with partially decoupled systems and things like that. So take a look at those, and then we will come back together in like 15 minutes. Okay? Fly, be free. So the exam for chapter 2 is going to be on Wednesday. It'll be after class. I'll send out the file so you'll have access to the file, and then you will have until Sunday, the following Sunday, to finish it up. And I'm telling you, it's not very long. There's like 4 problems, so it's not a very long exam on purpose. It's only a 50-point exam, so it's short, all things considered, and short and sweet and to the point. But what are some particular skills and topics that you might want to review or think about before then?
Just everything to do with the writing the code, like all the commands and everything, and like what they need.
Okay, so Maple code, but specifically code for what kind of things? Give me an example.
D plots,
DE plots.
vector field plots.
And remember, DE plot, that's code for phase plane or phase portrait. And you've also got the 3D. So there's phase plane, there's phase portrait, and there's the 3D. And then vector field, that we get by doing, sorry, my dogs are deciding to play in this room. Direction field. And the weird thing is the old one, normally she doesn't like to play, but she's feisty all of a sudden. So what else? What are some other Maple code that we'd want to be familiar with?
Euler's method.
Yeah, Euler's method. And specifically, I don't know if you probably noticed that Euler's method for a system is actually easier code than all the hullabaloo to do that for a single equation. Right? So Euler's method for a system. What else? Anything else in Maple?
That scene.
Yeah, doing in a DE plot. How do you get a scene graph? What does that mean? What does that allow you to see? What else? How about just doing a desolve for a system? You remember, if you just do desolve for a single equation, you can get the general solution, desolve the equation, close parentheses, and you're done. But for a system, you have to put brackets around the system. You have to group things, right?
We got to remember our initial commands like with plots and with DE plots.
Yep. So your with stuff in there. So with DE tools, with plots to be able to get that vector field, direction field command. Yep. What else? Anything else in Maple? This is a pretty Maple intensive section. The good news is that a lot of this is going to translate over into chapter 3. We're going to continue to use this stuff in chapter 3. We're also going to learn some new stuff in chapter 3. Okay, so aside from the Maple code, what are some concepts or topics that you probably want to familiarize yourself with?
Decoupled systems.
Yeah, decoupled. Or partially decoupled systems, being able to recognize when you have one or the other, and knowing that you can solve them analytically, right? What else? What else came up?
The harmonic oscillators, like the
Yes.
damped.
Yes. So a damped harmonic oscillator. So if I showed you an equation like y prime, so m times y prime, double prime, plus b times y prime plus k times y equals 0, you should recognize that right away. That is an equation for a damped harmonic oscillator. Well, thank you very much. Oh, apropos of nothing, she just decided she's going to come in here and start playing in the background. So, anyways, sorry. What else? What else with damped harmonic oscillator? What should you be able to do with that second order differential equation?
Make a system of what are they called? First order equations.
Yeah. You should be able to convert to a system of first order. And you should also be able to find particular solutions using the guess. Yeah, the guess, and you should be able to guess at particular solutions. Since we don't have a way of solving them any other way analytically, that guess is really our best chance at finding a solution to that equation. Because if you turn that thing into a first order system, it's not decoupled in any way. It's not decoupled at all. So, anything else pop up? See, I don't have to worry because I don't have to take the exam. So I'm just writing stuff down here.
Using the matrices.
Thank you. I'm glad that came up. Yeah, being comfortable with the idea of a vector field as a matrix, right? And being able to write that system of equations as a matrix equation. And you don't have to get too fancy. So for example, if I gave you dx dt equals 2x plus y and dy dt equals, I don't know, negative 3x plus 2y or something like that, you should be able to rewrite that as a matrix equation. And wait for it, it's really complicated. Dx dt, dy dt, that's one matrix on the left-hand side, and that's going to be equal to another matrix on the other side, 2x plus y minus 3x plus 2y. That's all that I want from you right now. Really, truly, just being able to write it like this. And then recognizing that this thing right here, that's the vector field, right? That's how I would write the vector field values. That's how I would determine the vector field values. What's the vector at any x and y coordinate? Well, you plug it in here to get the x coordinate, plug it in here to get the y coordinate, or the behavior at the x coordinate and the y coordinate. And then you put it together and you can see the dx dt, the rate of change horizontally and the rate of change vertically combine to form an overall rate of change. That's the hypotenuse of that triangle. We're going to spend more time with these guys in chapter 3 though. Okay, somebody didn't warn me. We're past 7:40 and you didn't warn me. Paul, I'm blaming you. You're normally the one who tells me I need to turn on the record. So here's what I'm going to do. I'm going to stop sharing, and then I'm going to stop recording. So that's it for the video.